Oh, if only it were that simple. The search for extraterrestrial life is analogous to trying to find the needle in a haystack. If you don't actually know what the needle looks like, what a needle even is, or if it's there at all for that matter. Don't worry though, there are around 100 billion fields, each containing around 100 billion haystacks to look through, so there's probably a needle in there somewhere, although we can't be sure. Also, I lied a bit at the start because you're not even looking for the needle at all, because that's too hard. Instead, you've chosen to look for signals that may or may not be produced by the needle, but can also be produced by lots of other things, so it's not really that helpful. And did I forget to mention that it'll cost you several $1,000,000 to look at just one haystack, of course, provided someone else has already paid several $1,000,000,000 to make and set up the equipment and is happy to let you use it. Oh boy, this is going to be a tough one. So how do we find aliens? Our current method is launching telescopes into space and looking for and at lots and lots of exoplanets. We currently know of almost 5,000 confirmed exoplanets, discovered mainly using space telescopes such as Hubble and TESS, with this number growing ever larger. By far the most successful method of finding them is looking for transiting exoplanets, whose orbits pass between us and their host star. This would result in a periodic dip in the brightness of the star, due to the exoplanet blocking some of the light. TESS, the Transiting Exoplanet Survey Satellite, rather unsurprisingly uses this technique, and has discovered over 4,000 candidate planets. However, this method is also open to many false positives, such as brown dwarf stars transiting a larger star in a binary star system, which translates to only around 100 of these being confirmed exoplanets. Transits will also only occur once every exoplanet year, so detecting a periodic drop in brightness naturally takes a long time. Fortunately, our efforts are in no way wasted, as in analysing the light received from a star during and between transits, we actually receive a colossal amount of data, allowing us to deduce a number of different properties such as planetary mass, planetary size, orbit, orbital distance, temperature, and atmospheric composition. Let's look at a couple of these. The method of finding planetary size makes use of the percentage change in brightness during a transit. When relatively close up, the amount of starlight that the exoplanet blocks is heavily related to the distance between it and an observer. We can see that the angular size of the exoplanet is proportional to the arc cot of the distance from it, causing its size to vary greatly for short distances. However, when we are sufficiently far enough away, the graph asymptotically approaches zero as the photons that travel from the star to Earth are all roughly parallel. Consequently, the amount of starlight that the exoplanet blocks can be modelled as a function only of the size of the exoplanet. Thus, the ratio of the drop in brightness to the initial brightness is a good approximation of the ratio of the cross-sectional area of the exoplanet that we see to the cross-sectional area of the star. This cancels down to the ratio of the squares of the two radii, which we can use to calculate the volume of the exoplanet, provided we know the radius of the star. To determine the mass of the exoplanet, we can use the Doppler technique. This makes use of the fact that planets do not simply orbit around their stars, but instead around the common centers of mass of the star system. This causes the star to wobble slightly around the center of mass, giving it an oscillating radial velocity towards and away from Earth, which we can observe from its redshift and blueshift. If we plot this on a curve of Doppler shift against time, we get information about eccentricity of orbit, mass, and orbital distance. Asymmetry in the curve denotes high eccentricity, a high amplitude can suggest a high mass, and the frequency relates to the orbital period of the planet, from which we can calculate orbital distance using Kepler's laws. During a transit, some of the star's light will pass through the atmosphere of the exoplanet and interact with the chemicals present there. These interactions with atmospheric particles leave chemical signatures in the spectrum, corresponding to the discrete frequencies of light that different chemicals are able to absorb or emit. If we compare the spectrum during and between transits, we can get information not just about the composition of the exoplanet's atmosphere, but a number of other atmospheric features. For example, absorption lines can translate to negative temperature gradients as the atmosphere cools during the trajectory of the photon, whilst emission lines can suggest positive temperature gradients. We can even discern the existence of clouds from both evidence of Rayleigh scattering, responsible for the scattering of blue light in Earth's atmosphere, as well as lower amplitudes of spectral features of water. Armed with this myriad of exoplanet data, we can now begin to use this information to find life. For this, we consider the planet's habitability and see if it satisfies a given criteria, allowing us to narrow down the search to focus on just the top candidates for sites of extraterrestrial life. One of the biggest properties we look for is the ability to sustain surface liquid water. Water is important as it acts as a good solvent and is liquid over a broad temperature range, making it an extremely useful fluid in which chemistry can occur. Further, and most importantly, all life on Earth requires water to survive, so we assume that this is a necessary condition for alien life as well. The catch is that this is nothing more than an assumption, as we have no other sites of life to test this hypothesis on, and thus our definition of habitability is extremely prone to bias. The conditions we look for that we deem necessary for life are what we have extrapolated purely from a single data point, life on Earth. Despite the extraordinary richness and complexity in the biology of Earth life, Biological laws that appear universal here cannot necessarily be applied at the cosmic scale and be expected to be obeyed. Thus, the notion of habitability that governs where we look and what we look for may be blinding us from the true extent of the diversity of alien life. Nevertheless, our time and resources are severely limited, and to maximize their use, we sadly cannot afford to look at everything. This line of thought is what gives rise to the search for biosignatures, chemicals that are produced mainly by biotic processes on Earth and are therefore indicators of life. An example of this would be oxygen, which is produced primarily by plants in photosynthesis and makes up 21% of our atmosphere. Currently, we have confirmed the existence of 8 exoplanets with O2 in their atmospheres. Does this mean we have found life? Well, no, because there are also abiotic processes, which can produce oxygen and could also be responsible for this. A strong indicator of life would be the coexistence of 2 biosignature gases that react with each other, giving an unstable state of chemical disequilibrium. An example of this would be the presence of both oxygen and methane, which we have here on Earth. In this case, if life were not the cause of this, abiotic processes would have to produce both of these at a high enough rate that sufficiently exceeds the rate at which they are destroyed to allow for a detectable equilibrium amount, which is highly unlikely. Our search for biosignatures is mainly conducted with infrared spectroscopy in the low IR range. Molecules such as water, carbon monoxide, methane, carbon dioxide, ammonia, and oxygen all have distinct spectral features in this range. We can see these features in the Earth-shine spectrum with a distinct drop at around 0.77 micrometers, corresponding to absorption by atmospheric oxygen, as well as 3 major troughs between around 0.9 and 1.5 micrometers, which are spectral features of water. Back at around 0.7 micrometers, we see the red edge, a sudden spike in reflectance corresponding to the wavelength at which the chlorophyll pigment stops absorbing light. Searching in the IR range is extremely useful for being able to identify similar features in exoplanets, as well as lessening the extent to which light from the exoplanet is drowned out by light from their host star, which emits more light in the visible and UV ranges due to their higher temperature. Next-generation telescopes, such as the James Webb Space Telescope, will be able to identify these features better than ever before, continuing the legacies of their predecessors Hubble, Kepler, Spitzer, and TESS. With a mirror diameter of 6.5 meters, the JWST will be able to analyze the atmospheres of exoplanets to greater detail, allowing for more accurate data on their composition and relative abundances of different chemicals. As of today, we have discovered 4,796 confirmed exoplanets, 46 of which have atmospheric water, and 6 of which also have oxygen and methane. The focus lies on around a dozen of these, including the Proxima Centauri and TRAPPIST-1 system. To guess the probability of us finding life in the near future is futile, in the sense that we have very little idea of how prolific life in our universe is. However, assuming that it is there, we are looking, and it is not at all inconceivable for us to make a discovery within the next 20 years.